finally, in section 5.2, part 3, we look at it's a task in which what formula to use is up to you, right? So you need to be able to decide which is the correct formula for the problem you're working on. So a reminder that when you're making periodic payments and you're given the periodic payment amount, you either have a future value of an annuity or a present value of an annuity. On the future value side of things, you have no money in the beginning, you're making those periodic payments, and you have a lump sum at the end. For the present value of the annuity, you're using the money up front. You need the money today, now. You're making those periodic payments, and at the end of the time, you'll have zero left as a balance. Okay, let's take a look at 3 examples, see if you can decide which one is which. So on the handout for section 5.2, this is example 3. It says if Jackson deposits $150 at the end of each month in a savings account, earning interest at the rate of 6.5% per year, compounded monthly, how much will he have on deposit in his savings account at the end of 10 years, assuming that he makes no withdrawals during that period? Take a second, see if you can figure out whether it's a future value or a present value. So because he's trying to save money up and he's putting the account in every month for 10 years, and he needs the money at the end, and it says how much will he have on deposit in the account at the end of 10 years. So that makes this a future value problem. Future value. We know that he's doing $150 every month. That's our conversion period of 12 for 10 years at an interest rate. So our formula becomes S is equal to R 1 plus 0.0. Sorry, let's write the formula down, then we'll plug the numbers in. R over M to the MT minus 1 all over R over M. So plugging the numbers in, R is the $150 he's going to put in every month. 1 plus 0.065 divided by 12 to the 12 times 10 minus 1 all over 0.065 over 12. And now you're heading to the calculator. Once you're all done calculating it, your end answer should be $25,260.47. Now, if you just put the $150 every month into account, let's see, how much would you have then? 150 times 10 times 12. He'd only have 18,000. So by doing the interest, he's gained an extra $7,000 in interest alone. So that's why you invest big. Okay, example 4. So example 4 tells us that both Kathy and Andrew are salaried individuals, 45 years of age, who are saving for their retirement 20 years from now. Kathy makes a $1,000 contribution annually on December 31st into account at 8.25% per year. She makes a contribution annually, so she only makes it once a year. At the same time, Andrew makes $100 payments monthly into a tax-deferred annuity, paying 6% per year compounded monthly. Which individual will have more money at the end of their investment? So because they're asking us for the money at the end, we know, again, that it's a future value. And so we're going to do them one person at a time. So we'll do Kathy first. So Kathy is doing $1,000. So that would be her periodic payment. She is doing it annually. So we know that's once a year. Her interest rate is 8.25%. So 0.0825. And she's going to do it for 20 years. So T is equal to 20. So for Kathy, we're going to have S is equal to the $100,000. I get the right alphabet soup in here. 1 plus 0.0825 divided by 1 to the 1 times the 25 years minus 1. And that is all over the 0.0825 divided by 1. And then you head to your calculator, type it all in. And you should end up with Kathy having $47,049 Not a bad chunk for her 20 years. Whoops, oh yeah, sorry. She's only doing it for 20 years. Hopefully you caught that. So this should be 20. I'm not watching what I'm doing over here. So it comes out to be $47,049.14. Now Andrew, he's going to make his monthly. So in a single year, Andrew is actually depositing more because he's doing $100 every month, 12 times a year. Still for the same 20 years, his interest rate is at 6%. So it's a lower interest rate. So more payments, but a lower rate. So what does he end up with? So we're going to do the $100. 1 plus 0.06 divided by 12, because it's now monthly. 12 times the 20 years minus 1 all over 0.06 divided by 12. And he ends up with $46,204.09. So even though he is depositing more per year because of his lower interest rate, he ends up with about $2,000, about $1,000 less, a little less than $1,000, $800 less in the account. So Kathy ends up with more money in the account at the end of the 20 years. Okay, our next example, example 5, talks about a car and a car loan. Example 5. After making a down payment of $3,000 for an automobile, William paid $325 a month for 48 months with the interest charged at 5.75% per year compounded monthly on the unpaid balance. What was the original cost of the car, and what portion of William's total car payments went towards the interest charge? So I've got two questions going on here. So let's write down the information. We know that he put down $3,000. Now that's not going to go into the calculation until the end of everything. He is paying $325 a month. So that month tells me our conversions is 12 in a year for 48 months. So that tells me 4 years. And the interest was 0.0575%. So because he needs the money now to buy the car, and at the end of the loan he owes 0, we know that this is a present value formula. So we're going to switch gears on our formula. So present value, need money now. Okay. So the formula is R 1 minus 1 plus R over N negative MT. This is that negative exponent again. All over R over N. Keep wanting to put the numbers in. Do you notice that? For R over N. Okay, now we'll put the numbers in. So his monthly payment is $325. The interest rate was 0.0575 divided by 12 to the negative 12 times 4. And again, that's that 48 months that he's paying. So 0.0575. Then you head to your calculator and calculate that out. And you're going to end up with $13,906.37. Now, that's the loan amount. So that's how much he's borrowing. They want to know how much he's paying for his car, what the purchase price of the car is. Well, don't forget he put $3,000 down. So we're going to figure out the car price. We're going to add those two together. So the car price is going to be the $13,906.37 plus that extra $3,000 as a down payment. So he bought the car for $16,906.27. Okay, it goes on to say or ask the question, what portion of William's total car payments went towards the interest charged? Well, let's stop and think. If he's paying $325 a month for 4 years, let's do it times 12 times a year times 4 years. In other words, how many payments did he actually make of the $325? So if you do that, you get $15,600. So this is the dollar amount that he's paid back. So that's the amount paid back. Well, he only borrowed $13,906, but he paid back $15,600. So if we take the $15,600 and subtract off how much he borrowed, we're going to get how much was left over in terms of just interest. So how much interest he paid on the loan. So he ended up paying $1,693.63 in interest. So in order to borrow the money from the bank, that's how much interest he ended up paying for the privilege of borrowing that money. And that wraps up our annuities, both present value and future value. Our final section in chapter 5 deals with what we call sinking funds and amortizations. And the only difference is in the formulas, instead of knowing the periodic payment, that's what we're going to be looking for. So it takes both the present value and the future value formulas and solves them for R. And those are sinking funds and amortizations.